so we're now moving on with our gear study here, and we're going to talk about the transmission of torque and force. All right, so the first thing we're going to do is we're going to do some free body diagram on our gears. Okay, so right here we have a point of contact, and we're going to assume that it's just about at the center line of the pitch circle. All right, so right where those two tangent points. Now it's not quite there, but we're just going to assume for this analysis that it is, because of the involute design. No matter where it contacts, it will have the same effect. Okay, so what we have essentially here is we have a tangential force, Ft. All right, and then we have a radial force. You can see that they're at an angle of our pitch diameter, or not our pressure angle. So we're going to have forces pushing the two gears apart from each other. All right, and that's an important thing. So that's our radial force. All right, and that's pretty much the two things that we need to have to do our analysis. So there are basically two equations that guide our analysis. All right, and that is our tangential force. And this is based on the torque that we're inputting. Has nothing to do with speed. And that is going to be equal to the torque over the diameter. And that's the diameter created by these, the circular pitch, theoretical diameter. And we're going to divide that by 2 since we are using a radius. So we'll just put that up top. All right. So for the sake of just showing you to put some numbers with this, I'm going to make up some numbers. And I'm going to say that's 5. And I'm going to make it inches. And this is 250 inch-pounds of torque. So I will get 100, pounds. All right, and I carefully chose those numbers so we get exactly that amount. All right, the second thing we'll do is we get the radial force based on the tangent, because we have a line here. We know that is 14.5 degrees. Our radial force is equal to Ft times the tangent of theta. All right, and if my math serves me correctly, we will get 26 pounds. All right, so for every 100 pounds that I'm actually transmitting from this gear to this gear, I'm getting 26 pounds pushing away. So you can already see that there is some inefficiencies here. So not that it's really practical, I just want to point it out, but there's a total force here. And that is equal to the square root of the sum of the squares. So Fr squared plus F tangent squared. Now, if you're like me, you can actually do this another way. You can say that it's equal to the tangential times the cosine of our angle. All right, either way we get, 103.3. All right, which makes sense. It's bigger than 100, but that 26 pounds really doesn't change it too much. It's only about a quarter of the value. So there you have it. So I'm going to write these numbers down over here, and then I'm going to erase other things. So this is for Spur gears, by the way. And now I've saved that data and I've erased everything else because I want to move on to helical gears and how they're different in the calculation. Okay, so if I have a gear, right, and I have teeth here, and it's turning about this axis right here. All right, as I'm turning, I've got a nice flat width. I've got a constant profile for my teeth. However, if I make another gear, but I start cutting all my teeth, and we're just going to say that our teeth here are at a 20-degree angle. All right, so that we're going to label that as our variable psi. And what happens here is we start getting a different tooth profile when we look at it in different ways. So when we look at it from one point of view, let's just take a section here, and we'll just call this section A. All right, we're going to get a profile that looks like this. And right here, our pressure angle is phi. We're going to add in phi tangential. But that's not quite the case. Notice how in the view perpendicular to it, that's where we keep our angle. All right, that's the specified angle, the pressure angle. All right, when we start rotating this, and I'm going to do a partial section here of B. Let me label this one A. All right, we got B. We're going to have it's going to look just about the same. All right, but when we do our pressure here, we're going to get a different angle, and that's theta n. So we have three angles here, and they're all related together. We've got psi, we've got phi tangential, and phi normal. And there's an equation that relates them all together, and I'm not going to go through the trigonometry, but they are related in this way. The cosine of psi is equal to tangent of theta n, phi, excuse me, I wrote that as theta, phi n over the tangent of phi t. All right, now we know two of these. One of them I already said was it's 20 degrees. And this one is 14.5 degrees. And make sure when you're using your calculator that you are in degree mode and not radian mode, because you'll get completely different answers. All right, so what I'm going to do is I'm going to erase this, and then we're going to start writing out other equations and figuring out what the forces are on that gear. Whoa, that was magic. I jumped to the other side of the screen and the board erased itself. That's creepy. Okay, so it's going to work a little bit differently. We're going to need to kind of back into one equation. So our first thing is going to be, we need to find the total force. So our tangential force, which we know, is 100 pounds. All right, we're keeping that because that's the only thing that resists that torque. We're going to say that it is equal to an unknown force times the cosine of phi n times the cosine of psi. Oops. Okay, so we know that, and we could back solve here, and I've already done the math, but F equals to 109.53 pounds. All right, and I brought that up to 5 significant digits, although I don't need to. I only have essentially one in the first one. So we will do that anyway, just to be more accurate. Okay, so right away, by definition, these two match up. Okay, now let's look at the radial force. And that is equal to the sine of theta n. All right, so F times the sine of theta n, and guess what? We're going to get exactly 26 pounds. All right, so those two line exactly up. All right, now before we go calculating the total, we now cut those gears at an angle. So we're going to get not only the tangential pushing against the end of the gear, and the radial pushing apart, but we are actually going to get an axial force shoving the gears sideways, and they're going to be obviously shoving each other the opposite direction. So we're going to have an FA, and that is equal to F times the cosine of theta n times the sine of psi. Yep, that's right. All right, and if I do the math there, I'm going to get 36.4 pounds. All right, so I've actually added in a pretty significant component there. So I want to make sure that whatever bearings I have, they know that that load is coming, and we do that, whether it be a tapered roller bearing or some sort of thrust bearing on the end of on the face of the gear. I want to make sure I can take that. All right, now for our total force. Well, we already know it. It's right here. All right, so we have this new component and our force. So while that and that stayed the same, our total force went up simply because we added in another axial component. So the last thing you're going to want to know is what kind of horsepower am I looking at in these gears. So my power in horsepower is going to be equal to a tangential force in pounds times my surface velocity in feet per minute. I'm going to divide that by 33,000 to get the correct units. Now, if you're using something like MathCAD, which I highly recommend, you can put this in pounds, put that in a feet per minute, and get that out no problem. Thank you for watching this video. We hope it was helpful to you, and appreciate you coming to us, and we ask you to subscribe. Thanks. Bye-bye.